Hey, hello. In the era of AI, GPU is the dominant hardware for training our model. As a software developer, I think everyone should know something about the GPU hardware architecture in order to better utilize this hardware to accelerate our code. I believe many people have heard of the concept like a grid, a block, and we all know that the GPU has many threads, thousands of threads, and also there's a different kind of a memory hierarchy, global memory, shared memory, and also local register, and how we utilize this to do the calculation we want, how the acceleration or data parallelism really happen. This is the content I'm going to introduce to you in this video. Hopefully it will be helpful for you to better understand the hardware architecture and better to accelerate your code. Let's jump to the content. So as normally the way how I make a video, in this particular video, I'm going to use the example. Here I choose a very common example and very well studied problem. That's general matrix multiplication. We're going to use this one to demonstrate that how this task is handled in parallel. And when come to the grid and block concept, uh, how this task is divided by using this concept, and we will be better understand that how the hardware really separate the task in a distributed manner. Because as we all know, GPU is a distributed hardware. It has many core, different kind of CUDA core, and also it has a lot of streaming multiprocessor. So there's a good reason to understand how the computation work is shared by this many hardware in order for us to better utilize this hardware. So let's first try to understand uh, matrix multiplication and how we can parallel those matrix multiplication on GPU. So assume here we have a two matrix A and B, and we want to time them to calculate matrix C. So based on the basic matrix calculation, the result of C will be m row and n column. And when we calculate it, each element in C is calculated by the first by a row in A matrix and by a column in a B matrix. So what we do mathematically, we're doing the dot product between these two vector, and then the dot product result is a scalar, and this scalar will be put here. So if we look at the total workload, we can think about an example. Assume that M is 8,192 and N is also the same dimension. If we want to calculate this C in total, we need to do this amount of calculation for each of the elements. So this is the total workload we need to do. And how do we divide this total workload on GPU? And this is the role of this grid and block concept come into play. So the grid and block concept, they're mainly used to help us to divide this amount of total work into the thread unit we have there. Ideally, if we use the GPU to do calculation, we would like to have each of the work handled by one thread, and then we will achieve our maximum parallelism, right? So, but in reality, the hardware is limited. It doesn't have that many physical thread or CUDA core to do the job. So we need to somehow separate them into different kind of block. So the grid is actually the top level one, and under the grid, we will have uh, the block. So basically, the block is under the grid. If the grid, th then inside each of the block, we will have a number of a thread, right? So we will have a multiple thread inside. So this is more like a hierarchy, multiple thread inside a block and multiple block inside a grid. When we launch a kernel, a grid is launched for us on the hardware. The key thing we need to remember is that the one block can only reside on one SM. This is the stream processor. We can't have one block across multiple SM. So, so this actually somehow gave us the limitation here, because if one block has to reside on one SM, that means the resource inside the SM should be enough to handle this one block work, right? So each block, we need to use some resource to do the calculation and some memory for that. We need to make sure that the block size we gave here is actually enough for this one SM to handle. So this is actually the whole reason why we need to start define our block size in the first place. So if you look at the way normally how we before we launch a kernel, we always first start by defining the block dimension. This is the dimension for one block. In this case, we have 16 times 16. That's 256. That means inside one block, we have a 256 number of a thread. And this is actually related to the SM resource. We know because we implement the kernel ourselves, and we know that inside this kernel, how much memory we're gonna consume, and we also know that for each of the streaming multiprocessor, how much memory is available. So based on this relationship, we can roughly estimate what's the maximum number of or the size of one block this SM can handle with this resource. So that's why we always start by first defining the block dimension for one block, then using this information to further calculate the grid dimension, right? So because in total, as I mentioned, our workload is IM times n, this much of work, because we need to calculate each of the elements in parallel. So in order for us to estimate how many grid we need, we will use the block first. Now we know each of the block can handle 256, this amount of a thread. So what we need to do is simply to divide, right? To divide uh, uh, the length of m and n with the size of the block here. So then with that, we can calculate how many grid we need. And this information will be passed to the kernel to do the calculation. So that's actually the whole principle. We always, just to repeat one more time, we always start by first figure out the block size, because this is more like a hardware restriction. Once we're given a GPU, we know that there's a limited resource for one stream multiprocessor, and one, as we mentioned, that one block can only reside on one stream processor, and this is the reason that we can only um, make sure that the block size or the block dimension we are given here is enough to be handled by one stream multiprocessor. That's the idea. So now I want to further elaborate this idea by showing you the CUDA code and also having the GPU architecture next to it, so we can somehow establish the connection for each of the step that which part of the hardware module is involved, right? So for this part, this is the thing we explained in previous slides, that we need to define the block size. As I mentioned, this block size is associated with the hardware limitation of this one. So just one thing to remember is that it's not necessarily associated to the CUDA core. So the yellow part here, this is the CUDA core. We may not have as many as this 256 amount of number of CUDA core in one SM. So the way how GPU handles it is more like the CPU way of handling the context switch. So if we have a multiple thread running there, and then the context switch means that okay, we also have a memory next to it. What we could do is that we could actually support more than we have in hardware by saving the state of the thread into the memory, and then switch the contact to another group of thread. So in that sense, it looks like we have a multiple thread, more thread than the physical, but in reality, we handle this thread in a sequential way by switching the contact and loading the data from the memory to the thread. Those data we load includes the variable value, the instruction, and all those kind of things. This is actually similar like how CPU handles it, right? So once we define this one, then we actually have the grid dimension as well. Then we start to launch the kernel. Then this actually comes to the kernel side. This will be run. This code is the CUDA code. It will be run on GPU. And by the way, this is the host code. It will be run on CPU for sure. And then what we have here is based on the block ID and the block dimension, and also this thread ID, we can calculate the row and the column. As you probably remember that we have this matrix multiplication, right? So here and here. Then the output is the C. We have A here, then B here, and then C here. We're calculating each of the elements by doing the dot product, right? So this is actually the way how we do the dot product, right? Uh, by basically time them up first and then accumulate the value. So this is a standard way to do the dot product. But we actually need to figure out which row in A to use and which column in B to use, right? Because this is actually I, this is actually J, and then we have IJ here accordingly. So this block ID and block dimension, and also there's a thread ID, it helps us to figure out which row and which column we use, because our idea is to let each thread handles one of these calculations. So in total, we will have a AMSTEM n thread. I mean virtual thread, not really the physical thread, but the virtual thread, as we can support by this hardware to do the work for us. So then, in order for this particular, when that virtual thread execute there's a CUDA code, you need to figure out which row and which column it needs to load from the memory. In this case, we're loading the data from the global memory here. So as you can see, we actually have the pointer A and B and C. AB is mainly for load and C is for store. So this is how we execute this one inside one thread, and this and also using the block ID, thread ID, and basically the virtual way how we divide the task uh, to figure out how many row and how many column or which row and which column this particular thread need to handle. So that's basically how we separate the matrix multiplication and handle that in a parallel manner. Hopefully this is helpful. But probably as you noticed that we haven't talked too much about the memory hierarchy because there we have a shared memory as well. This shared memory is accessible by a block, and all the thread inside a block can share the same shared memory. So this is actually pretty helpful to reduce the amount of time we need to access the global memory, which is very slow. I'm going to make another video to explain how this memory access coalescing works. The whole point is to reduce the memory access to the global memory because the slowness, and we want to utilize more of this shared memory. And there's also another concept called a warp. This warp is actually also a concept that used by the scheduler to schedule that how many threads need to be executed together in terms of the instruction. So I will also make a separate video to explain that one. But yeah, thank you for watching and see you next time.